Alright guys, this is our next fun sheet or fun sheets. There's two, you got two in class, and I'm going to break the videos down, and as I get moving here, we'll see if it becomes two videos or three. It's a lot of information, and a lot of it's review in the beginning, and we're building on all the stuff we've been talking about for weeks. Alright, so this is the standard PS 1.4, analyze and interpret chemical reactions to determine if the total number of atoms in the reactions and products support the law of conservation of mass. So that's a whole bunch of information in that standard that we're going to break apart into smaller chunks. Alright, so the first batch is a bunch of vocabulary words that you should know most of these. Several of them are review. Some of them are new. So coefficient is the big number in front of the element. It tells how many of the entire substance. So I knew I couldn't fit the word substance on that line over there, so I moved it below. Substance. Alright, the subscript then is the small number behind or below the element. It tells how many of that atom. Reactants we've talked about since like October. Reactants are the substance initially present in a chemical reaction. They're what's on the left side of the equation. Then we have the arrow or the yield sign in equations. It's sort of like the equal sign. When you read an equation, remember we had H2O plus CO2 plus sunlight yields or produces 6O2 plus C6H12O6. So that arrow is the yield sign. And then we had the products, which if you remember from that equation that I just said, are on the right side of the arrow, and it's the substance that is formed once the reaction is complete. And then there's this word precipitate, and you've seen this word several times now. When we first started talking about chemical and physical changes, and we did that breakout, you saw the word precipitate, and we've seen it in experiments, but you need to know that it's a solid that's created in a chemical reaction. So like an example would be potassium chloride. Those are both liquids when they start, and when you pour them together, they make a solid. I jumped the gun there, sorry. Covalent compound is a compound that shares a pair of electrons, usually one metal and one nonmetal. That's why it's important for you to know where your metals and nonmetals are on the periodic table and to be able to look and use your periodic table effectively. An ionic compound is when electrons are transferred to the other atom, and ionic compounds usually form with two nonmetals. And when we talked about Bohr's diagram and then the electron dot diagram, and I said the electron dot diagram will be important when we start making compounds and combining our elements and our atoms, this covalent and ionic compounds are examples of that. Alright, when that will come in handy, I guess. And then there's diatomic molecules. And diatomic molecules are two atoms of the same substance. An example is oxygen. Remember when we were doing photosynthesis equation and we did that whole big song and dance thing, and the people were on one side of the classroom yelling oxygen and the other people on the other side of the classroom were yelling glucose, and I said oxygen always go in pairs because those are diatomic molecules, and diatomic molecules are always together, and oxygen is one of those. And then hydrogen is another example. And we'll talk more about all these terms coming up. All right, Chemical reactions. Substance change identity. You know this. We talked about this when we were doing chemical reactions and chemical and physical changes. You know that that's a way to tell. They break and form new bonds, and it involves valence electrons. I've heard that word before. I wonder what that means. What does valence electron mean? You should write it down right here. All right, clues to chemical reactions. Gas formation or bubbles. Remember when we did the experiment in the lab and we had the baking soda and vinegar and the balloon, and we dumped them in there and the bubbles formed? That's a chemical reaction. Precipitate or solid forms. I told you about potassium chloride. Color change. During that same lab, when we talked about, Miss Foshi and I did the demonstration at the front of the room, and we had the 2 bottles that we put food coloring in, and then I poured a substance in there and I swirled it around and the color went clear. That was an example of color change. And then finally, energy change, light, sound, or thermal energy. Remember on that same experiment when you dumped the vinegar into the baking soda and it blew up the balloon and we told you to feel the bottom of the bottle and it was cooler? That was energy change. Alright, so now let's talk about chemical formulas and what they represent. Chemical formulas represent a combination of elements. Example, H2O. That's 2 elements. It's 2 hydrogens and 1 oxygen. It's a shorthand way of writing substances using their chemical symbols and numbers. For example, down below here, we have 2 H2O, and that means there are 2 molecules of water or of H2O. So when we break this apart to see how many atoms there are of each, we have to know how to read it and how to use these numbers that are there. This 2 is the coefficient, and this 2, oops, I didn't mean to scribble on it. This 2 is the subscript. Also terms we just defined. So there are 4 atoms of hydrogen. And how do I get that? I think I show you here. It's 2 times 4. We take the coefficient and we times it by the subscript. So that gave us 4. And then there are 2 atoms of oxygen. And if you follow that blue arrow, you see, or this purple one, we took the 2 from the coefficient and times it by O and got 2 atoms of oxygen. The element itself is like 1. It's understood that there's 1 of those. So unless there is a subscript or a coefficient with it, you know that there's 1 of that atom. And you know 2 times 1 is 2. Alright, so to find the number of atoms, we go through several steps. First, you write each symbol down and what it represents. So you would write H for hydrogen and the word hydrogen, and then you would write O for oxygen and the word oxygen. You find the subscripts for each element. So H2O, the 2 would be the subscript. If there's parentheses, you multiply the subscript inside by the subscript outside. We're going to do examples of these. I know this is kind of wordy. It's sort of like math. You know, math is the language of science. These 2 subjects go hand in hand. You know, please excuse my dear Aunt Sally, the order of operations, that's sort of where this comes in handy here. When the distributive property comes in here. If there's a coefficient, you multiply the total number of each element by this number. And so we're going to do some examples. So for carbon dioxide, there is 1 carbon because this is just the C by itself. I just told you if it's by itself, it's 1. And then, I might draw all over this too. And then there's 2 oxygens because of this subscript right here. All right, next, I got a little ahead of myself. Let's look at okay, so NH4, SO4 is ammonia sulfate. And so looking at breaking this one down, we have, so then there's a subscript 4 for the hydrogen, so we know there's 4 hydrogen there. Plus, you have to distribute the subscript outside the parentheses, so 4 times 2 is 8, giving us 8 total hydrogen. Now we're going to look at the sulfur. There is just 1 sulfur, it's by itself, so just 1. And then oxygen has the subscript 4, so there's 4 oxygen. So you have 2 total nitrogen, 8 total hydrogen, 1 sulfur, and 4 oxygen atoms in that molecule or compound. Alright, now you're going to talk about rubbing alcohol is 2 C3H8O. So there we have carbon, and I circled it. You have the 2 as your coefficient, and then the 3 as a subscript, so 3 times 2 is 6. Then we have the hydrogen, and there's 8 next to the hydrogen, so then you have the coefficient again, and so we have the 8, like I said, and the 2 times 8 equals 16. Then we have the oxygen, and there's 1 oxygen, and then you're going to times it by that coefficient, which is 1 times 2 equals 2. So there you have 6 carbons, 16 hydrogens, and 2 oxygens. Now see if you can do the aluminum sulfur oxide on your own. So aluminum, oh whoops, I skipped it. Go back. So do the aluminum sulfur oxygen on your own, and we'll check it in class. Alright, naming compounds and molecules. Determine each type of element. Is it a metal or non-metal? This is where your periodic table comes in handy again. Knowing your groups and your families. You need to determine the type of compound. Is it ionic or covalent? And remember, we talked about this in our terms. If it is ionic, it has 1 metal, 1 non-metal. I like to think of the I looks like the number 1. And so that's how I remember it's 1 metal and 1 non-metal. And then covalent is 2 nonmetals. You're going to determine the number of each atoms. Determine number of the atoms of each substance. So that's how you name compounds and molecules. So then you have to write the name of the first element. Always change the ending of the last element to IDE. If it's a covalent bond, you add a prefix to show the number of atoms, and we're going to do examples of prefixes below, but those are for covalent bonds only. And of course, like everything else, there is an exception to the rule. If the first element has only 1 atom, you do not add a prefix. And if it's an ionic bond, charges must cancel each other out, and we'll talk about those later. Alright, prefixes for covalent bonds only. I think you did a activity in Miss Renner's room where you did prefixes. Mono, di, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, nona for 9, and deca for 10. These should be familiar to you. You've been using prefixes like these for words forever. Octa, 8-sided, like an octagon or an octopus. Pentagon, 5-sided building in Washington, D.C. You know, you've seen all these words before. All right, chemical equations. So what happens in a chemical reaction or change? So what happen? It shows what happens in a chemical change / reaction. It requires no translation around the world. It's like a recipe. Ingredients need to produce a cake. We've talked about this when we talked about photosynthesis, that the stuff that you have as your reactants produce a product in the end. And we're going to talk about this calcium plus sulfur. So those are the reactants. Label them on your paper. The arrow is said yields or produces, and then it is your product over here on the right hand side of the arrow. And then that's what's created. Alright, so we have calcium and sulfur react together to produce calcium sulfide. And you notice from our rules above, we had the IDE ending added to our second term there. Alright, diatomic molecules. We talked about them when I defined them. 2 atoms of the same substance. Includes hydrogen, oxygen, fluorine, nitrogen, bromine, iodine, and chlorine. When we write those, and when they're in equations, and when they're in reactions, they're always together. I want to say when they're alone. We always see them together. They travel in pairs. Remember when we did photosynthesis, and I said the oxygens always travel in pairs? This is that example. The oxygens always travel in pairs because they're diatomic molecules. If an equation like below, when there's a chemical equation for water, H2O2 is the 2 molecules that you're combining to make the compound H2O, and you don't write the second 2 on the O because when those combined, it loses the other O. That one that is lost is released as energy. So that oxygen on the product side is lost as energy, is what I just said. So this was a lot. We're done for this page. I know there's more notes on your note page, but that's going to be a second video. And we are going to do examples together in class of writing equations and naming compounds and elements, and compounds and molecules. Make sure you wrote everything I did. I know this was long, but it wouldn't hurt you to rehear these terms. And make sure you listened for the secret message because there was 2 in there.